I know a constable. That was fun. Oh. Get my mic up here. So, how are we doing this morning? Are we hearing me? Evidence of this working?
Yeah.
Okay, cool. Thank you. So, battle plan today is to start chapter 10, unless there are any questions about chapter 12 that people would like to talk about first. And I would be totally fine with that. If there are questions, that would be awesome. But if there aren't any questions about chapter 12 or proceeding, as it were, then we will start in on chapter 10. Not hearing anything. And I should say, in case you somehow haven't noticed, this is the next to the last week of classes. Holy moly, how does that happen? We have nearly survived the exciting experience of online education for half a semester, and that's pretty awesome. And I appreciate everybody's patience and cooperation in these strange and crazy times. The final will be similar to the midterm, and I'll pass that out next week. One of the things that we would normally do this week or next week is course evals. Obviously, we are not all together to do that. My understanding is that you have been sent an email with a link specific to you as an individual that lets you access course evals for all of your courses. And that this happened, I think, a week or more ago. So you can do them whenever up to the end of the semester. I don't know actually when they'll close that. I would assume probably the end of next week, maybe into finals week, but I wouldn't count on it. I would probably better if you assume that it will be the end of next week, unless you know different. And if you do, feel free to tell me. So yeah, you should do that. We definitely appreciate feedback from students. And I think especially, I mean, under any circumstance, we appreciate feedback from students, but I think especially at this weird time, knowing like what worked and what didn't and how we did would be really very helpful. Fingers crossed, won't have to do this again in the near future, if ever. But it's possible things will go weird over the summer and we're doing this in the fall. Please don't make that be true, but you know, it could happen. But also, like, for me as a individual, I've never really considered teaching classes like 1302 online before. I mean, it's come up in conversations, and I've always been like, well, you know, I like doing it in person, and I don't know if that would make a lot of sense as an online course. Well, you know, here we just did it, or at least half of it, which sort of proves it's at least possible. Now, whether I want to do this more regularly still, I think is unclear. I think I would rather teach people in a room, frankly. Actually, I know I would rather teach people in a room. Yes, proof by contradiction in action. But that doesn't mean, I mean, it does mean that this is demonstrated that it is at least possible. That could mean, for example, that if I wanted to do this as a summer class online, I could. Would that be what I want to do with my time in the summer? Maybe not, but you know, it opens a door. So knowing from you folks like how successful this was or wasn't, strengths and weaknesses, so if it would happen again, like how we could do it better, et cetera, et cetera, et cetera. All of that stuff would be very valuable and greatly appreciated. So if you've got a second and can do the evals, that would be awesome. If you can't seem to find yours, I'm not sure who you talk to about that. You could talk to me first, and I could try to chase down who actually to talk to. Um, but they can't come to me because I'm not allowed to see them until grades have been turned in, and because I'm not supposed to be able to punish you for saying mean and terrible things about me or providing useful feedback. So okay, so there's all of that babbly. I'm working on the midterms. I'm approaching halfway-ish. I think when I get to around halfway, I'll probably release the scores as far as they are, which will hopefully happen today if I can avoid a meeting or two that want to suck me away. So you should have some feedback by today. And this is my top priority at the moment. So I'm hoping that by tomorrow I'll have them done. Kind of depends on how long some things take. But definitely working on that. So go ahead.
Yes, I had a question relating to that because currently it says in the Canvas that it's only partially graded. So
So does Canvas say it's partially graded?
yeah, it says I have like an 8 out of 42 currently.
Really?
Yeah,
I
not and
That's interesting. I
that
mean, that's probably right. I mean, given how much it, because I suspect I did two problems, and then I'm going through and doing another two problems. So I'm doing them kind of in groups, and I haven't finished the second two problems. So it's likely I did the first two problems for you, and you got 4 and 4 on those two problems, which is good. Yay. And like I said, hopefully I'll have the next two done. I've got the next two done for quite a few people, but not everybody. And I'm guessing you're in the not everybody category. And I thought things were set up so that you couldn't see anything, but that's clearly not true because you were telling me things that make sense, which imply that you can see things. Can you actually see the feedback, or can you just see that it's partially graded and that this is the score?
I can only see the grade that you gave and the rubric for the two scores that you graded. So
When I saw
Huh.
mine, I saw feedback. Like
Did
I saw
you?
you, yeah, I saw that you said that yeah, like a correction for a problem.
Okay. Well, then apparently it's visible. I could swear Canvas, because I actually checked, and I was pretty sure Canvas was like, no, they can't see anything. And, well, okay, obviously. Me and
I
Canvas
was
are not fully in
yeah,
agreement.
I was just asking because I was concerned.
Yeah, no, I mean, that's part of why I wanted to control the revealing of partial scores, because people legitimately kind of freak out when they see that they got 8 out of 40 and they're like, oh my God, did I just completely fail the exam? And it's like, no, Nick just hasn't graded most of it yet. So thank you very much for telling me, because my assumptions were wrong and I definitely don't want to be misleading or confusing people. So this tells me that you're actually probably going to be able to watch me grade the exam, as it were, in that your grade will just go up in chunks as I go through and do your exam for whatever set of problems I'm currently working on. I will definitely send a note on Canvas and Slack when I finish the exam, so you'll know that it's actually done. And that the score that's there is the actual score and not sort of a partial score. But yeah, thank you definitely for letting me know that that was happening, because my understanding of the world was clearly incorrect. So I appreciate the feedback.
Thank you.
So thank you. And if you've got questions about any of the stuff, definitely let me know. Also, I shared a full set of solutions to the exam weeks ago. So you can always look at that if you're uncertain about what you might have done differently. And questions are always welcome and appreciated. So, okay. Are there any other questions? Okie dokie. Then we are going to commence into chapter 10. So chapter 10, in some ways, is kind of why it's the best argument for why this is a computer science class and not a math class. Everything else we've done could have just been in a math class. Now, it probably wouldn't have been done the way we did it. Like the approach we've taken has had a definite computational flavor in places, but chapter 10 would almost certainly not appear in a traditional math book. It is a very computational thing that's going on in chapter 10. In chapter 10, we're talking about how we can prove the correctness of computer programs. And so we're using all this stuff that we've done in logic and quantifications and blah, 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 to get to this point where we can actually talk about what does it mean in a formal way for a program to be correct. And this is, I think, a very profound thing, because most of our experiences with whether programs work is by poking at them, right? We write a piece of code and we try it. Maybe we try it in a formal way, in the sense that we write automated tests that run the code and confirm that it works on certain cases. Maybe we check it by just running it a bunch by hand and going, yeah, it seems to work, right? But these are never proofs of anything. A test shows you that it worked for a particular instance, but it doesn't show that it will always work. And if you've got a blind spot in the way you think about your tests, that blind spot means that there could be a place where the code's not going to do what you thought it was going to do. And you're not going to be aware of that because you didn't have a test that caught that possibility. And so if we really care about correctness, an actual formal proof of correctness is the strongest thing we have going. Now, in fairness, we don't do this a lot in computer science. It turns out that we don't have great tools still. I mean, the ideas have been around for decades, but our tool support is still pretty tough for doing big proofs. We can do little things like we'll do in this class, but the tools that we have don't scale well to proving the correctness of really big systems. And so we don't tend to use them as much as we could, right? And we can discuss the sort of politics and sociology of that. But it's a true thing that we don't do a ton of proofs. There are environments where proofs are considered a necessity. So there are environments where failure can clearly lead to very bad consequences. And there can be expectations of that people do proofs or some sort of formal correctness arguments because there are circumstances where we don't really like it if planes crash. NASA uses formal proofs to prove the correctness of certain parts of their control software because, again, the cost of failure is very high and very public. There are medical devices where there, excuse me, where there are formal correctness proofs so that medical devices don't kill people, because that would be bad. So there are cases where this is done in a very formal way, but they're the exception rather than the rule. As a sort of just, average software developer, you're probably not going to need to do stuff like this, but knowing that it's possible has value. And also understanding some of the logical meaning of common constructs in computer science, I think makes you a better programmer. So I think this is all very valuable, even if you won't probably do a lot of correctness proofs in your future, okay? So that was a lot of babbly setup. Are there questions about any of the babbly setup before we actually start doing stuff? Okay. Questions? So I'm going to share my screen. Whiteboard. Share. Okay. Let's go to black.
Nick,
Yes.
I came a little late, but you said the grades the exam is being continuously updated, correct?
Correct.
Okay, yeah.
Yeah. So if you've got, 10 out of 40, don't freak out because it just means I haven't graded but a handful of problems.
Yeah, I missed that part. I just checked and it didn't look good.
No, that's all cool. That's all cool. And I know it's kind of freaky if you look and it seems like you're getting some tiny, tiny number of points and you thought, I didn't do that bad. That is entirely legit.
Thank you.
Not a problem. Other questions? Okie dokie. So the first thing we're going to have to go back and remember from way back at the beginning of class, there was this idea of Hoare triples where we had Q followed by program S leads to R. And the basic idea here is we said if Q is true, oops, that's not a big Q, that's a little q. If Q is true, and that's the precondition, and we execute program S, we find out at the end, then R is true when S terminates. And that's the post condition. Okay. And here, Q and R are predicates. So things with Boolean values. And S is a program. And we don't really know what it means to say S is a program because we haven't defined what programs look like. At the moment, that's just an assignment statement. Because that's all we've got. We'll actually introduce some other pieces, if statements and while loops, as we go through chapter 10. But for now, a program is just assignment. That's all we have to work with, okay? So this, I hope, looks at least dimly familiar. We may have forgotten, repressed memories of the details, but hopefully this looks at least like something we've seen before from back at the beginning of the semester. So we'll use this idea to create what we're going to call specifications. And a specification is going to look something like Q is precondition. We have a program that assigns some value to X where we don't know what that value is yet, and that leads us to R. And so the way to think about this is that some program that assigns a value to X. It may do other things, but one of its consequences should be that it assigns a value to X, satisfies, oops, can't spell. It's right the first time. Satisfies this specification, i.e., if we run the program starting in a state where Q is true, when the program terminates, R will be true. Boom. So a specification like this is just saying, this is the precondition, this is the postcondition, the thing that needs to be true when the program finishes. And this part in the middle is saying, well, what are we assigning values to? What variables are we going to update in the program? And a program satisfies this specification if we can put this program in here and the Hoare triple will be true. If we start with Q being true and we run the program, then when we're done, R should be true. Okay? And we'll do some concrete examples next, but are there questions about the sort of vague, big picture-y part of things?
Since we don't know what a program is, wouldn't we just, well, I'll just do the examples. I'm confused. So
Yeah, and so, I mean, at the moment, all a program will be is assignment statements. We'll talk more about how we would build a program as we go through the chapter.
Okay.
But we'll actually see some very simple concrete examples where we just have a single assignment statement, and we can see that a program that with a single assignment statement can move us from some precondition to some postcondition. And then we'll expand that out to include if statements and while loops, so we have like full, fancy programs. Does that help a little?
Yeah.
Okay. And definitely keep pushing back if you're like, yeah, this is a lot of abstract weirdness and I don't really get how this connects to anything. Like, definitely keep telling me that, because that's useful to know. Okay. Okay. So let's look at an example, because I think that would help a little. So let's consider example. This is an example from the book where we have 0 at most n. The program assigns some value to D, and the post condition is that D squared at most n less than D plus 1 squared. And the book says this is that a translation of this into English is the program computes an integer approximation to the square root of n. 4, and at least 0. Now, I think it's entirely legitimate to be like, what does that even mean? How does this have anything to do with square roots, etc.? So I want to talk about that for a second. I just want to fix my rather messy bit of writing there. There we go. That's a little better. Okay. So this is saying, and Abdi, to sort of get to your point to some degree, when we're looking at a specification, we don't care what the program looks like. The specification is saying, this is formally what the program does without getting into how it does it, right? So in some sense, we're going to be good managers here. We're not going to micromanage the program and tell it how to do what it's supposed to do. We're giving it sort of the job description. This is what you need to accomplish. We're not going to worry right now about the details of how you get that work done, okay? And if you want to break it up into pieces and do it in pieces, if you want to hire somebody else to do the work and give them some of your money, if you want to look it up on the internet, whatever, we're not worried about that right now. We're just saying that this program, whatever this program is, should get us from this precondition to that postcondition. So that's the first thing to be aware of. When we're looking at a specification like this, we don't care what the program is. We don't even care what's possible about what programs look like yet. At the level of the specification, we're merely saying that there is some black box that gets us from here to there. It assigns a value to D through whatever mechanisms work for it. It can consult a psychic or, just make things up. Now, how you would prove anything about that, I don't know, but somehow it assigns a value to D that gets us from the precondition to the postcondition, and that we don't have to care at the level of specification what this looks like yet. We'll open that up and talk about what that might look like as we go through the chapter, but right now when we're just talking about specifications, it doesn't matter. Does that make sense?
Yeah. So we're kind of like just staying on the abstract level right now.
Absolutely. In a very abstract way, actually. So then we say here that this computes an integer approximation of the square root of n. What does that even mean? Well, if we think about square root of n, obviously, square root of n. The square root of 25 is 5. That one's pretty straightforward. Now, the square root of 24 is something weird, right? It's like 2 times the square root of 6, whatever that is. And, square root of 26 and 27, those are, strange numbers as well. So this is something a little less than 5. These are going to be something a little more than 5. We generally don't like dealing with real numbers in computer science. Real numbers, actually, floating point numbers have a lot of issues. We don't deal well with them. We can't represent them exactly. There's a whole host of issues there. So it's not uncommon, actually, to work with what we would call integer approximations of things. And here, all we're doing is if this is 4 point, I don't know what, blah, 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 then we're going to map this to just 4. We're going to like throw away the decimal point parts and just get 4. And if this is 5 point blah, 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 we'll throw this away and map this down to 5 as well. And this is 5, blah, blah, blah. We'll map that down to 5. And we'll keep going until, we get to 35. That's going to be 5 point something. 36 will be 6 point something, or 6 even. And 37 will be 6 point something. So this will be 5, this will be 6, this will be 6. So we're going to think about the integer approximation of the square root to be the largest. So the integer approximation is the largest integer d such that d squared is less than or equal to n. So 4 is the largest thing where largest integer where 4 squared is less than or equal to 24, because 5 squared is bigger than 24. 5 is the largest thing where 5 squared is less than or equal to 25. It's actually equal to 25. 5 is also the largest integer that is whose square is less than or equal to all of these numbers. 25 is less than 26 down to 35. If we went up 1 to 6, it would jump all the way to 36. 36 is not less than 27. So 5 is our best approximation for the square root of 27, because 6 would be too big. And then 6 becomes our best approximation of the square root of 36. It's not even an approximation, it's an exact value. And it's also the best approximation of the square root of 37 and 38, and et cetera, and et cetera, et cetera. And that's all that this tells us. This is essentially this. Because we're saying that d squared is less than or equal to n. That's this part here. And this captures the largest part. If d is the largest value that makes this true, then one way to capture that is to say that d plus 1, the next integer, is too big. That if we square it, we're no longer less than or equal to n, we're actually strictly bigger than n. So this is a way of specifying that d is the largest integer such that d squared less than or equal to n. And that's what the book means when they say that it's an integer approximation for the square root of n. Questions about that?
So just to clarify here,
Yeah.
Because I think I had everything in my head wrong just until you mentioned that part. So essentially, the thing that's kind of the actual variable here is d.
Correct.
I mean, looking back at the problem as a whole, that seems really obvious. But yeah, so okay.
Right. So n is sort of given from the outside, and we are finding the value of d that makes this true in relation to whatever n we were handed.
Right. Gotcha.
So if we were handed 35, we would find that d should be 5. And again, we're not talking here about how we find that d is 5. We're not worrying about how this happens. But through whatever magic, if we hand this 27, we ought to get that d is 5. And if we hand it 24, we ought to get that d is 4. And if we hand it 37, we ought to get that d is 6. So
Right.
d is the thing we are computing based on whatever we were handed as an input, which was n.
Okay.
And the precondition here that n is at least 0 is important, because if n is less than or equal to 0, then square root of n doesn't make any sense. And in particular, there is going to be no d squared less than a negative number, less than or equal to a negative number. So if this was like -5, we're not going to find any value of d where d squared is less than or equal to -5. So that's why we need this precondition. Without it, we're never actually going to be able to find a solution over here. Okay, does that make sense?
Yep. Gotcha.
Other questions? Oops.
So D is a program that assigns a variable and we're looking for the variable, or is D the variable that we assign stuff to?
So D is the variable we assign things to. So N is sort of coming in from the outside, and D is the thing that we're going to assign something to as a way of saying, here's the answer. So if you imagine you're like a little elf sitting in a room, and there's a slot where people slip in numbers they want you to compute the square roots of, n is going to be what comes in the slot. You're going to do some computation. We don't know what you do. You can consult an oracle, or maybe you just look it up online or whatever. And then you pass out an answer, and that's going to be D. Assigning a value to D is your way of passing an answer back to whoever wanted an answer to the question.
Okay, then in that like example, the elf is in D, correct?
The ELF is the program that assigns a value to D through whatever means that it chooses to.
Okay. Okay. Yeah.
So the ELF is the program, N is the input in this case, D is the output, and the ELF is the program that does the work.
Okay. Okay. Yeah.
Does that make sense?
Yeah, that helps. Thank you.
You're very welcome. Questions about this before we look at another set of examples from the book? Going. Okay, I'm actually going to stop sharing the whiteboard and share a different window, and then we'll come back to the whiteboard when we're done with this example. But there was a nice example in the book that I didn't want to have to write all of this on the whiteboard by hand because I figured we'd be here for a month watching me do it, and that didn't seem to be a good thing. So here this is from, where is this from in the book? This is the bottom of page 180. I'll actually write that, page 180. So this is 4 different specifications that all do essentially the same thing, but in different ways that are important and worth talking about. I should also point out, I actually did a little repair work here because my scan got kind of messed up over here because this is where the pages come together. And so the focus got all kind of mangled here. So in the book, this is correct. I just, rewrote it or retyped it so that it would look a little more readable than it did in the scan. So in all of these, we are assuming that that B is an array. So B is an array of n values. Now, we haven't really talked about arrays very much. So let me say a little bit about that. So B, you can think of it as a sequence of values. So it's a way of having a group of values together. So if I wanted a collection of the exam grades for Sally, where I wanted to keep them separate by problem, this might be Sally's grade on problem 0, Sally's grade on problem 1, Sally's grade on problem 2, up to Sally's grade on the last problem on the exam. So it's a way of keeping a collection of things together in a little bundle, okay? And we access the pieces by their index. So B square bracket 3 gives us X sub 3, okay? And all of this starts at 0. That's a thing that you got to keep clear in your head, is that we're using 0-based indexing. So B of 0 is the first value. Oh, stop it. What have I done? I clicked something and a bad thing happened. Okay, sorry about that. So value, oops. Okay. And then B of 1, or B of n minus 1 is the last value. Okay. So that's what we mean by an array. It's just an indexed collection of values. And if we provide an index in square brackets like this, we're saying we want a particular value out of this collection, out of this array. If you've done a little programming, this will look familiar. If you've not done any programming, that's fine. You should definitely ask questions if it's unclear. Okay. Now, one other thing I'll say here, and then we'll actually move on to the example itself. The book uses a notation which is very convenient. So the book says X is in B of I dot dot J is shorthand for there exists K, I at most K less than J, B of K equals X. So this is just saying that there is some spot between I and J equal on the left and not equal on the right, where the kth element is X. So that there is some value in this section of the array that is X. So that if I want to say 2 is somewhere in the array, I could say 2 element of B0 to n. And 0 to n would be the entire array. And that would say that 2 is, there is some K somewhere in there that is equal to 2. So I can say that 2 is in the array somewhere. And similarly, if I do a not element of, like they do right here, that's just a way of saying this is not in the array anywhere. Okay. And we'll, as we go through this, we'll see examples of this. So if you have questions as we go along, definitely ask. Okay, questions about where we are before we actually start talking about all this book text? So all 4 of these specifications, there's 4 specifications here. Here, 1, 2, 3, and 4. All 4 of these specifications in some way say that the program, the elf, the genie, whatever it is that's sitting here, who we don't know anything about, the program should find where the first place where X is, or some place where X is actually, some place where X is in the array. Okay, like, so we've got an array of values. We're trying to find where X is in that array. And this is actually a very common kind of problem in computer science. You have a big collection of stuff, and you're trying to find a particular item in the big collection of stuff. As an example, when you log in to the university's computing systems, then, whoa, what happened there? That was super weird. When you log into the, oh, that is so strange. Okay, sorry about that. When you log into the university's computer systems, then you log in with, say, your X500. The university has this vast ocean of people that could log in. The university has to figure out, well, in that vast ocean of people, which one is you? Like, how do we find you in that big collection of people? And if, for example, we have your X500, right? We've got a lot of people. Can we find your find you using your X500 somewhere in all of that stuff? And the university's got to look through all of the people and find the person with that X500 or that ID number. And to do that efficiently is very important. You've got to, because with millions and millions of people, you don't want to just be doing that in a stupid way, because that would be really expensive. So this question of finding something in an array is a really common problem that comes up all the time in computer science. And so we care a lot about problems of this sort. And this is looking at 4 different specifications that all, in different ways, speak to this question of how do we say that we're trying to find a value in a collection. Now, my computer is acting weirdly on me. So I'm going to actually stop sharing and reshare for a second, because the chat window came up and is sitting right on top of what I need to talk about, and I can't read it. So I'm going to stop sharing and then hope that that fixes the problem. Let's reshare. And yes, Noah, that is my cat. Oh, all the notes went away. That is super annoying. I was worried that that was going to happen. Apologies for that. Hopefully, well, I'm not going to try right now to repeat all those, but as we go through, if there's ever a like, what was that question, definitely ask, and we'll sort of scribble in the margins again. So bad me. And whoever just said something in chat, I'm not going to actually look at it right now, because I'll be right back in the same place. So if it's important, like, actually make noise if you can, rather than the chat, because this is not sharing and the chat are interacting badly. Questions? Okay, so the first one says, our precondition is that X is in the array somewhere. So X, oh, come on. There we go. X is in the array. Because this is the beginning of the array and this is the end of the array. This is a way of saying we're looking at the whole array. So X is somewhere in the whole array. Our program will assign some value to I. And the post condition is that I is going to be between 0 and n. So it's going to be a legal index. So we're inclusive on the left and exclusive on the right. So I will be a legal index, and X is B of I, so that the ith value will in fact be X. Okay? Does that make sense? Like, this is a great place to ask a question. So we're saying, let's assume that X is in the array. The elf will assign some value to I. And when we're done, I will be a legal index and X will be B of I. So I is going to be the location of an instance of the value X. Now, this assumes here that X is in the array at the beginning. Often when we're doing searching, we don't know for sure that X is in the array. If I provide the university with a random number, that may or may not be a legal student ID number, for example. Maybe it's a number that's never been assigned. Maybe it's a number outside the range of legal values. Maybe it's the number of somebody who's been removed from the system for some reason. I don't think the university actually removes people from the system for various reasons. I think it may mark them as inactive, but I don't think it actually removes you. So I don't think that's super likely, but you know, it could happen. So often we want to do searching where we don't know for sure that there is something in the array or in the collection that has the value we're looking for. So here, we're just going to assume that n is greater than or equal to 0, that there are 0 or more items in the array. The elf does the thing and assigns a value to I. And when we're done, one of two things is true. Either it found it or it didn't find it. If it found it, what does that mean? It means I is a legal index and B of I is X. So the ith position has the value we were looking for. Or it didn't find it. How are we going to indicate that? Well, what they do in this example is they set I to be N. So N's not a legal index, right? It's off the end of the array. N minus 1 is the last legal index. So we're using I equals N as a way of flagging the fact that we didn't find it. We got to the end, didn't see it, okay? So we're saying I is equal to N, we didn't find anything, and X is not in the array anywhere, right? Because we need this part, we need the X is not in the array, because if we didn't have that, we could just automatically set I equal to N and return, like not bother looking at all. We could always just say, no, they're not in there, even if they are. So we don't want to allow the program, the ELF, to cop out by always saying, didn't find it, and returning without actually confirming that, yes, indeed, the value we were looking for was not in the array anywhere, okay? So either we find it, we have a legal index, and the value at that index is X, or we didn't find it. There is no X anywhere in the array, and we set I to be N as a way of indicating that fact. So that's a kind of a weird specification. People have questions about that? Okay. Then the next two have similar preconditions. We're not assuming that X is in the array, and they have different ways of indicating that we failed to find the value. Here, we're saying that I is a legal index. Oh, that should be an or. So that's actually a typo. Or. X should be, I is a legal index, or there is no X in the array, and X is the ith value, or I is N. Turns out this is actually the same as that. We could use chapter 3 rules to show that you could rewrite this to be that. There's a P and Q or R and S rewrites to this thing from chapter 3. So these are just two different ways of saying the same thing here. I don't know quite why you would prefer the second one. To be honest with you, I think the first one makes more sense to me, but the book's just trying to make a point. So questions about that one? I'm not too exercised about the third one. Now, the fourth one's interesting, though. The fourth one says we're going to assign values not to just I, but to I and C. Oops, sorry. And C is going to, so far, we've used this sort of I equals N as a way of flagging the situation that we didn't find a value. Now we're actually going to create a new variable, a Boolean value, that we're going to use to indicate whether we did or didn't find an instance of X in the array. So the ELF now is giving us two things back, I and C. And C is saying, I found it or I didn't. And I is, this is where it was if I found it, okay? If I didn't find it, I make no promises as to what the value of I is. But if I did find it, I will be where it is. So C is equivalent to X in the array. So if X is in the array, C will be true. If X is not in the array, C will be false. So that's the specification of C. And C implies, so if C is true, i.e. we did find an instance of X, then X will be B of I. So that would be like this thing here. So if we did find it, then I is the index of an occurrence of X. Okay. So all of these are different specifications of essentially the same idea. They just organize it in different ways. Okay. The first one is actually different than the other three because it assumes that X is in the array. The other three do not make that assumption, and they all have to indicate in some way whether they found X or not as they went through the array looking. Okay. Questions about that? That's a lot of stuff. Okay. Now I'm going to stop sharing this screen and go back to the whiteboard. So are there questions about this screen before I have it go away? Going, gone. Okay, now we'll go back to sharing the screen. Whiteboard, share. Okay, so now things will hopefully behave themselves a little better, and I can see the chat again and not have it hate on me, which is nice. So yes, I like our cat too. He's a sweetie pie. He's not very bright, but he's sweet. So, okay, so so this, excuse me, this is all still pretty abstract. And given that it's 10:11, we're not going to get to like a full-on example until Friday. But so what I'll do now is highlight one other weird, well, not weird, but one other notational device the book uses that's important. And then we'll sort of end there, and then we'll actually do some examples of proving the correctness of actual very, very simple programs on Friday, okay? So this last thing to talk about is this idea of rigid variables. So often in programming, we have a situation where we want we know X has some value, and we're going to assign a new value to X. And what we want to say here is that X went up by 1. Or X was doubled. Etc. So our post condition is going to need to say something about how X changed relative to what it had been before. So we need to be able to say that X is 1 more than it used to be, or 1 less than it used to be, or twice as much as it used to be, or whatever. I mean, there's some relationship between the new value of X and the old value of X. And for that to work, we need a way of giving a name to the old value of X. And that's where this idea of rigid variables comes in. So the book says that if we have X is, and then they use a typewriter font. Actually, I'm gonna use a different color because I can't make typewriter font easily. I will attempt it anyway, but you know, realistically, I'm not going to be like great at doing typewriter font. So I'll do this brown color, and I'll try to use that as my typewriter font as a way of indicating that I'm doing a rigid variable when I do one. So that'll slow things down a little bit because I got to keep switching colors. But so we're saying that X has some old value typewriter X. Okay. And then our program is going to do something to little x. And when we're done, X is going to be typewriter X, typewriter X, the old value plus 1, if we think in terms of increment as an example. So this is saying X is now 1 more than the old value. I.e., we incremented X by 1. And this, giving this name here in the precondition, allows us to talk about the new value of X in relation to the old value of X. So this is the new value, the value that the ELF gave us back, and this is the old value. So essentially, we have to keep track of the old value so that we can see how the old value and the new value compare. If the goal is to make sure that we have added 1 to the old value, we need the old value still around somewhere. We need a name for the old value so we can make this comparison. And so this precondition is a way of giving a name for the old value so that we can refer to that in the post condition. Does that make sense? A little bit. Sort of, maybe.
Is there any way that you can like refer to it from the post condition, or does it have to be like, is it a post condition or precondition requirement to have the old value be referenced in there? Yeah.
So essentially, in the current universe, the way the book sets it up, and this is how most people do it, you do have to give a name in the precondition in order to have some way of referring to it in the post condition.
Okay.
Now, there are other ways that this is sometimes done, but for our purposes, for the week and a half that's left of the semester, we're going to always, if we need the old value, we're going to give it a name in the precondition, and then we will refer to that in the post condition.
Sounds good.
Okay. Other questions? Great question. And we could do other things. So we could, as another example, we could say, if X is, and again, switch colors, old value of X, and switch colors again. This is not as fast as I would like. Apologies. And we assign X some value. Our post condition might be that X is 2 times the old value of X. So this might be saying that we want to double the value of X. So we want to double the value of X. Boop. Okay. Does that make sense? Questions about that?
I was just wondering, so why don't you like for the precondition, I mean the post condition, why don't you put like the big X in front of like where the little X is, and then put the little X next to the 2, and then.
Right. So you're sort of asking, why is it not this? Is that correct?
Yeah.
So this would be saying the old value is twice the new value. So this is basically saying X is half of what it was. So if the old value was, say, 6, we're saying the new value is 3, right? So we would be saying that the new value, the value the elf gave us back, would be half the old value. Whereas over here, we're saying that x is 2 times big X. So we're saying, like, if this is 6, then this is going to be 12, right? So if the old value was 6, the new value needs to be twice that. The value the elf gives us back needs to be 2 times the old value. So it needs to be 12. So you could do this, what you said, but that would mean something different. It would give us division instead of multiplication, essentially.
Okay.
Did that make sense?
Yeah.
Okay. So we're a minute past. I should shut up and let you go on with your lives. Does anybody have any super quick questions in the -1 minute that are left? Otherwise, we'll pick this up on Friday and we'll start doing some examples. I would encourage you to read at least the beginning parts of chapter 6 up to like the conditional, if at all possible. I think that'll make this make more sense. So we will see everybody on Friday. Thank you very much. We'll talk to you later.
Nick.
Yes.
So I have a question about my midterm. But
Yeah. So
I also have an office hour later. Do you want to just deal with that then?
Actually, let me have a quick look because I think I have the thing in front of me. Let me let me confirm that that's what happened, so that we can get it fixed. Okay, Justin Oberg. So yeah, so I've got a PDF that has problem 0, problem 2.
Yeah, if you go all the way to the end, you'll see the last problem 0, which I think you didn't see. That was just because my scanner wouldn't do two-sided.
Oh, I'm with you. Okay, yes. So you're right. You're not missing the 3rd and 4th one. I get what happened. Okay, so thank you. I will fix that before I do my next thing so that I don't forget that we had this conversation.
Okay. Otherwise, I have office hours at 4:30 about data structures.
Cool.
So
we can definitely talk
fun.
about it.
It's gonna be great. I'll see you later.
Okay, ciao. Bye.